All right, today we are talking about section 3.2, the product and quotient rules for differentiation, and also learning how to use our calculator to evaluate a derivative at a point and sketch the graph of a derivative. So our product rule says that if we're taking the derivative of a function times by another function, that the derivative will be the first function times the derivative of the second plus the second function times the derivative of the first. The quotient rule is a little bit more involved. This is taking the derivative of a quotient, so something with a numerator and a denominator. This rule says we're going to leave take the denominator times by the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So there's a lot going on with this rule, and I bet you're wishing there were some way to remember it. And lucky for you, we have a little saying. So for the quotient rule, we say low D high minus high D low divided by low squared. So low D high less high D low divided by low squared. So low just means the denominator, D is the derivative of the high, which is the numerator, less, so minus, the numerator, which is the high, D low, denominator of the derivative of the denominator, divided by the denominator squared. All right, let's see some examples of how to apply these rules. All right, so we are asked to differentiate f of x equals 3x squared minus 2 times 2x plus 3. So we're actually going to do this in two different ways. The first way that we're going to do it is with using the product rule. And then the second way we're going to do it is by simplifying first algebraically and then just using our power and constant multiple rules. So using the product rule, this is our first function. This would be like our f of x. And 2x plus 3 is our second function, or g of x. So to take this derivative, f prime of x is equal to the first, which is 3x squared minus 2, times the derivative of the second. So the derivative of 2x plus 3 would just be 2, plus the second, which is 2x plus 3, times the derivative of the first, which is just using our power rule, which would be 6x. So when we simplify, we'll distribute that 2, we get 6x squared minus 4, plus, distribute the 6x, 12x squared plus 18x. Combine like terms, we'll get 18x squared plus 18x minus 4. And that is our derivative using the product rule. Now, is there a way for us to make this so that we don't have to use the product rule? To do that, we would just multiply first algebraically, which we're not always going to be able to do. Later on, when we learn how to take derivatives of like natural log of x, you could have something like x cubed times natural log of x, and that's not something that we would be able to use algebra to get away from using the product rule. So let's go ahead and see this using algebra first and then differentiating. So algebra first, We can just double distribute. This will give me 6x cubed plus 9x squared minus 4x minus 6. Combining like terms, this, oh, we don't have any like terms. JK. So we can just go ahead and take the derivative of this. So f prime of x, no product rule needed here. 6x cubed, derivative using our power rule is 18x squared. Derivative of 9x squared using the power rule is 18x. And derivative of negative 4x is minus 4. And derivative of a constant is 0. So this is the same derivative that we got applying the power rule. Would this be the same answer if I took the derivative of each individual part? So the question is, does f times g prime equal f prime times g prime? So let's check that out. If I take the derivative of each individual part, we're wondering if we'll get that same, the 18x squared plus 18x minus 4. So the derivative of f of x by itself would be 6x. And the derivative of g of x by itself is 2x, which would give me 12x squared. These are not the same thing. So the answer to this question is no. All right, let's do an example of the quotient rule. If I can switch slides. Oh, I have to get out of this mode. Thanks for being patient. Here we go. All right, so if I want to take the derivative of this function, again, there's a couple of ways to do this. The first way that we're going to look at this is as a quotient. We have a function over another function. The numerator is going to be our high, and the denominator is our low. So we have low d high less high d low denominator squared. All right, so let's find y prime. So low is 2 minus 3x. Derivative of the numerator, or d high, is going to be 4x, subtract 4, minus high, which is 2x squared. And notice I put parentheses because it's going to be subtract this entire piece, not just subtract 2x squared. Derivative of the low is negative 3. All over low squared, or denominator squared, which is 2 minus 3x squared. All right. Simplifying this, we would need to double distribute on this first piece, so this would be 8x minus 8 minus 12x squared plus 12x, subtract, distribute this negative 3 to each term, which will give us a negative 6x squared plus 12x minus 9. And this is all over 2 minus 3x squared. Okay, simplifying the numerator. If I distribute the negative into each of those terms, it changes the sign. This will become a positive. Let's change this to red really quick. So this will become a positive, negative, and a positive. So combining like terms, we have negative 12x squared and a positive 6x squared. So that would be negative 6x squared. And then we have a positive 12x and a negative 12x, so those will cancel. And we have a leftover 8x over here, so plus 8x. And then we have our constants, negative 8 and positive 9 will give me plus 1 all over, and we'll just leave our denominator as is, 2 minus 3x squared. So this is our derivative, not with that too. That's our derivative using the quotient rule. Let's go ahead and see what this would, what another way to do this problem is without using the quotient rule. So we could algebraically manipulate this. Oh, go back. All right, here we go. We could algebraically manipulate this. The struggle. Okay, there we go. To become 2x squared minus 4x plus 3, and turn this into a product rule by moving this up to a power of negative 1. The only issue with this is we do have a power rule, so we could apply the power rule, but we have not yet learned how to take the derivative of more than one term raised to a power. So that's actually going to use something called the chain rule, so we'll come back to this after we've learned that unit. Okay, so with this you would have to use the quotient rule at this point. All right, let's go ahead and look at one more example using differentiation. We're going to use both the the quotient rule, and then see if we can do this another way. So using the quotient rule, negative 9 would be the high, and 5x squared is the low. So our derivative would be y prime equals low d high. So the derivative of negative 9 is 0. Minus high d low. The derivative of the denominator is 10x divided by the denominator squared. Simplification would give us 0 plus 90x over 25x to the 4th. And this is 90x over 25x to the 4th, which will reduce to 18 over 5x cubed. Did we have to apply the quotient rule? The answer to that is no. We can algebraically manipulate this to negative 9/5. So that's going to be like our scalar multiple. And then we're going to bring that x squared up to become x to the negative 2. And then this becomes very simple. It's just using our power rule. So y prime would be negative 9/5 times negative 2, x to the negative 2 minus 1, which will give me 18/5, x to the negative 3. And then since we started with a quotient, started with our exponents positive, we'll bring that back down. So this would be 18 over 5x cubed. Okay, so the point here is it's a good idea to see if you can algebraically manipulate a quotient to avoid using the quotient rule. Later on, when we've learned the chain rule, we'll be able to algebraically manipulate. Let's go back a little bit. Algebraically manipulate something that looks like this and avoid the quotient rule. We'll still have to use the product rule and something called the chain rule, but we will get there. All right, so the next thing we're going to do is talk about how to use your calculator to evaluate a derivative, and also how to use the calculator to graph a derivative. So let's take a look at this. Let's get out of this. Okay, so when you are in the regular calculator mode, you can go to the Math menu and you can choose option 8. So option 8, and my calculator is in something called Math Print. Math Print makes it look a little bit more like the actual way that we would write it. If your calculator doesn't look like this, then bring it to me and I can show you how to put it into Math Print. So let's say that we want to evaluate the derivative of f of x equals x cubed plus 3x. This is example 4 in the notes. So we want to tell our calculator that x is our variable, and here we're going to put, so this is where we put our function. So our function is x cubed plus 3x, 3 to the x. So that's x cubed plus 3 to the x. All right, now this won't find the actual derivative for us. This is finding the derivative, the value of a derivative at a specific point. So we're asked to evaluate f prime of 2. So we're going to tell our calculator to find us the value of the derivative at x equals 2. And then just press enter, and we get 21.8875 or 21.888. We'll just round that. Now, if you're asked to find the value of the same function's derivative at several different values, you can enter the function one time if you go to y equals, and let's say this is asking me to find the value of this natural log of x squared minus 3's derivative at 2 and 4. So I just want to plug that function in one time into my y1. So I'll have the natural log of x, x squared subtract 3. All right, so that function is saved into y1. So I'm going to exit out of the graphing mode. So I'm going to quit. And now I'm going to ask my calculator by pushing math, going to option 8, which is the derivative. And my variable is still x. But now instead of typing the function in, I can say take the derivative of y sub 1. So that's the function I entered into y sub 1. To get that, you're going to push the alpha button and alpha trace. Oh, that didn't quite work. Let's go back. So quit, try that again. Second, quit. All right, so we have ddx, and let's go over here. Again, alpha trace. All right, there we go. Alpha trace brings up this little menu right here, and I'm going, right now it's highlighted that I want option 1, which is y sub 1, and we'll push enter, arrow over, and put in the value that we want, which is 2, and hit enter. So we get 4.000. We can do the same thing. Go math, take the derivative, option 8 of d dx. Now instead of typing the function, we can go alpha, trace, select y sub 1, and now maybe we want to evaluate it at 4. And then we hit enter. And we get the value of the derivative at x equals 4 is 0.615. We can also see what the graph of this derivative looks like. So if we go to y equals, we're going to go down to y sub 2. Tell it that we want to graph the derivative, so math, option 8, with respect to x, of y sub 1. So we don't have to type that in again. So we hit alpha, trace, choose y sub 1. Now since we're not wanting just the graph of the derivative at a specific x value, instead of saying x equals some number, we're going to do x equals x. And graph. Now this is going to show me the original function, the y sub 1, and which is in blue, and the red is the graph of its derivative. So this is pretty interesting because this is showing us, remember that the derivative is the general formula for the slope of the tangent line. So the red is showing me what that would look like with all of those slopes for those individual points on the graph. All right, the last one, example 6, is to evaluate f prime of 0 for the absolute value of x. Now this one, the calculator is not going to give us an accurate answer. When you go to graph the derivative of the absolute value of x, so this is option 8, we can say d dx of math, arrow over to number to get absolute value of x, for x, and graph. We know that there's a sharp turn at x equals 0. And you can see that we have a break here in the graph. So we know that the derivative doesn't exist at 0. But if you were to go and ask to the regular mode, so let's quit the graph. Okay, if we try to calculate the derivative of the absolute value of x, make sure you're doing d dx, at 0, it tells us that it's 0. And we have to be a little bit smarter than our calculator in this case and know that f prime of 0 does not exist due to that sharp term. All right, awesome, guys. Thanks. So we will have a short quiz on this on, let's see, today I will see you guys. Just the next time we have class, we'll do a short quiz on product and quotient rule. All right, have a good night.